Hey guys, Mr. B here. In this video, we'll be going over the practice problems in Chapter 10, Section 1. Alright, so starting off with number 1, it says if 0.20 bushel is 1 dozen apples, and a dozen apples has a mass of 2.0 kilograms, what is the mass of 0.50 bushel of apples? Alright, so a lot of times in conversion problems like this, they give you a lot of information. And sometimes students get very confused because they're not really sure what number to start with or like what they should do with all this information. It's really important to figure out what is the number that we are starting with and what is the unit we're ending with, okay? A lot of times they're going to give you conversion factors in the problem, which you're going to need to use to do your math work, but you don't want to start with them. So let's try to figure out here what the actual question is versus what it is that they want us to do. Okay, so we have 0.50 bushel of apples. Okay, here's the question, right? The question is, what is the mass? Questions start with who, what, where, when, why, how, etc. Right? So if you like read all of this, there really is a question, and it starts right here at what. What is the mass? So our answer that we're going to give them is going to be a mass, which is probably going to be in kilograms, because that's the unit that they're giving us for mass. Okay, so we are going to have an answer of kilograms when we're done with this problem. So we're going to end up over here. Something is going to be equal to some number of kilograms. Now, the other question then is well, what is it that they want us to start with? So what is the mass of 0.50 bushel of apples? So we are starting with 0.50 bushel of apples, and we are converting that into some number of kilograms. Okay. Now this other information, like the 0.20 bushel is 1 dozen and a dozen has a mass of 2, that's all conversion factors. Okay, that's all just information we're going to use. So I'm going to switch my camera here to paper. So we're going to do this out on paper, and let's see how this works. Okay. So we have 0.50 bushel of apples. This is going to be equal to some number of kilograms, okay? And they're telling us that 0.20 bushel is 1 dozen. So 0.20 bushel of apples is 1 dozen apples. So that's conversion factor. That's right at the beginning of the problem. And then they also say that 1 dozen apples has a mass of 2 kilograms. So that's another conversion factor. So we're going to write both of these out. All right. So let's take a look at the unit that we're starting with and the unit we're ending with, and we're going to try to map out the units we're going to convert from. Okay. So we're starting with bushel of apples. And so in these two conversion factors we have so far, this one has bushel of apples in it. So we're going to go from bushel of apples to dozen apples. Bushel of apples will cancel out with these bushel of apples we're starting with will be in the unit of dozen apples. And then this conversion factor can go from dozen apples to kilograms, which is what our final answer wants to be in. Okay, so this is going to be a two-step problem. So let's set up a conversion table. Since we're starting with bushel of apples here, we're going to put the 0.20 bushel of apples on the bottom of our fraction. Okay, so this part of this fraction is going to be on the bottom. The 1 dozen apples will be on the top. We want the bushel of apples to cancel out with each other. So bushel of apples will cancel. Once we've used that conversion factor, we don't need it anymore, so we're going to cross it off. Then now we are in the unit of dozen apples. This conversion will go from dozen apples to kilograms. The way we've written it, though, we're going to need to flip it. We need the 1 dozen apples down here on the bottom of our fraction up in our math work, because we need that to cancel with the dozen apples that we have over here in this part of the fraction. Okay, so the 2 kilograms is going to be on the bottom, or sorry, on the top. So dozen apples will cancel out. And we'll notice that the unit we're left with, kilograms, is the same unit that our answer is looking for. Okay, so we know that we've done our math right. So now, remember, we're going to multiply all of these numbers along the top, and we're going to divide by all of these numbers along the bottom. Okay, so let me pull up my calculator here. I'm just using my phone, which is fine. Right, so we are going to take 0.50 times 1 times 2.0 equals, is that right? Yeah, okay. Divide by 0.20, divide by 1 equals. All right, so we get an answer of 5 kilograms. Okay, that is the answer that they are looking for. So let's go back to our notes here. We're just going to write in 5 kilograms because it's hard for me to type in the math work here and format it correctly. But anyway, okay, so this is our final answer, 5 kilograms. All right, take a look at number 2. This one is dealing with actual like chemistry units now. So this question is asking how many moles is 2.17 times 10 to the 23rd representative particles of bromine. All right, so let's insert a text box. You can do some typing. Let's change our font size. Let's change our font color. All right, so the question is how many moles? So our answer is going to be in moles of bromine, which is Br, okay? And we are starting with 2.17 times 10 to the 23rd. Oh, gotta remember hotkeys here. Times 10 to the 23rd. Representative particles of bromine. So the question here is what is the representative particle of bromine? All right, well, bromine is an element. So it would be in atoms of bromine. If, however, they were talking about bromine like gas, or bromine liquid, which would be found in nature, bromine is diatomic. It is one of the Brinkelhoffs. So it would essentially be bromine molecules because it would be Br2. Now, since they're just saying bromine here and they're not saying anything else, I'm going to assume that they're talking about regular elemental bromine. So this is going to be atoms of Br. Okay, that's the representative particle because bromine is an element. Elements exist as atoms. All right, so let's go to our paper here. Let's write out this information that we have and let's take a look at doing the math. So we've got 2.17 times 10 to the 23rd atoms of Br, and we are going to convert that into moles of Br. All right, so we need to ask ourselves, what is the conversion factor to go from atoms of bromine to moles of bromine? Now in this section we learned about Avogadro's number, which is the definition of a mole. So remember that 6.02 times 10 to the 23rd representative particles, in this case the representative particle is atoms of bromine, is equal to 1 mole of any material, which in this case is bromine. Okay, so here's our conversion factor to go from particles of bromine or atoms of bromine to moles of bromine. So this is going to be a one-step conversion. We're going to take this fraction, we're going to put it up in our conversion table. Since we're starting with atoms of bromine on the top of our fraction, we're going to want the 6.02 times 10 to the 23rd atoms of bromine on the bottom of our fraction so that they cancel out with each other. And the 1 mole of bromine then will be on the top because that is a unit that we don't want to cancel out. We want that in our answer. So atoms of bromine here will cancel out. And then math-wise, we're going to take 2.17 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. If you want to multiply by 1, you can, but it's not going to change anything with our answer. So on our calculator, we're going to go 2.17. And then to do the times 10 to the 23rd, there's this little double E button. Okay, we're going to use that little double E. So 2.17 double E 23 equals. Okay, so our calculator you'll see says 2.17 E23. So that means times 10 to the 23rd. We're going to divide that by 6.02, again, double E 23 equals. And this is what we get. Now we are going to keep track of significant figures. So our starting number was 2.17. That has 3 significant figures, which means we need to round this to 3 significant figures. So we're going to round this to 0.360. Okay, the 0 is our third sig fig, and that 4 is going to keep that 0 a 0. So our final answer here is 0.360 moles of bromine. Okay, that is what we are looking for. So let's box that in. We'll go and type that in on our notes here. Okay, so equals. This was 0.360 moles of bromine is our answer. There we go. Okay. So remember, the math work here is on my paper. If you want to do it on paper too, that's completely fine. I understand you can't really type it in here. So, all right, moving on to number 3. True or false? A mole of a pure substance contains 6.02 times 10 to the 23rd representative particles. That is true. That is, by definition, that's what a mole means. So that is true. All right, number 4. The representative particle of any compound is the molecule. That is not true, because molecules are only the particle for molecular compounds. Ionic compounds exist as formula units. So this is not true. This is false. This is only for some compounds. Okay, only molecular compounds. All right, number 5. How many moles of Pb is 9.3 times 10 to the 15th atoms of Pb? All right, so we have another conversion problem here. Again, if we take a look at it, we are going to be starting with 9.3 times 10 to the 15th atoms of Pb, which is lead, okay? And that is going to be equal to moles of Pb. So we're going from atoms of Pb to moles of Pb. This is pretty much just like the problem we just did with the bromine. We're going to use the same conversion factor. We're just basically starting with a different starting number. So let's go back to our paper here. Let's write this out. So 9.3 times 10 to the 15th atoms of Pb is going to be equal to moles of Pb. Since we are going from atoms or particles to moles, the conversion factor we want to use is Avogadro's number. So 6.02 times 10 to the 23rd atoms of Pb is equal to 1 mole of Pb. And then we're just going to make sure we set this up so that our atoms of Pb cancel out. So since we're starting with atoms of Pb here, we want the 6.02 times 10 to the 23rd atoms of Pb on the bottom of our fraction. And we want the 1 mole of Pb on the top of our fraction, because we don't want to cancel out moles of Pb, because that is what the answer is looking for. So atoms of Pb will cancel. We'll get into moles. Again, let's do it on our calculator here. So we will put in 9.3 double E 15 and hit equals, and it'll put it in regular format here, which is fine. So we can times that by 1, which isn't going to do anything, so I'm just going to skip that. And we're going to divide by 6.02 e to the 23rd equals. All right, now this is going to be a really small number, which is fine. We are going to round this to 2 significant figures, because 9.3 had 2 sig figs, so this needs to be rounded to 2 sig figs. So the first 2 significant figures are going to be the 1 and the 5. And we probably want to put this in scientific notation. But this is going to be, so this is 0. Let's see here. 1, 2, 3, 4, 5, 6, 7 zeros. So 1, 2, 3, 4, 5, 6, 7 zeros. And then 1, 5. Those are our first 2 significant figures. Moles of Pb. And then I'm going to put this in scientific notation just so I don't have to type all these zeros out. So we need to move this over 1, 2, 3, 4, 5, 6, 7, 8 places. So 1.5 times 10 to the negative 8th moles of Pb. That would be our answer in scientific notation. Okay, so this is what we're looking for. And that would make sense, because 1 mole is 6.02 times 10 to the 23rd, and we only had 9.3 times 10 to the 15th, which is like, you know, way, way less. So it would make sense that our number would be much, much smaller than 0. So, all right, so back in our notes, this is going to be 1.5 times 10 to the negative 8th moles of lead. Okay, so that is that's our answer that we're looking for. All right, moving on to number 6. How many atoms are in 1.14 moles of SO3? All right, so again, we are converting from, we're going from atoms to, or I'm sorry, from moles to atoms. So let's insert text box so we can type. Let's change our font size. Let's change our font color. All right, so we are starting with 1.14. That is not the size that I'm looking for here. Okay, 1.14 moles of SO3. And we are going to end up in atoms of SO3. Or just atoms. And here's, it's just going to be atoms. And here's why. So this problem's a little bit tricky, okay? But here's the reason why. We'll do it on paper here, and I'll explain why this is a little bit of a tricky one. So let's switch to our paper. Let's write this out. So 1.14 moles of SO3 is going to be equal to atoms. All right, now here's the reason why this one's a little bit tricky. We are definitely going to have to use Avogadro's number because we are starting in moles and we're going to particles. So we are going to have to use 6.02 times 10 to the 23rd. And remember that this has a unit, right? This is representative particles. So we need to think about what is the representative particle for this compound, SO3. This is a molecular compound, which means the unit that would go on this number is going to be molecules of SO3 because it's a molecular compound, okay? So that is 6.02 times 10 to the 23rd molecules of SO3 is equal to 1 mole of SO3. Now here's the reason why this is difficult, or why this is a little bit tricky. The answer they are looking for is not molecules, it's atoms. And the conversion factor we've written so far has molecules on it. So you might be thinking to yourself, well, okay, what do we do now? Well, remember that this is molecules of SO3. And by definition, a molecule is 2 or more atoms that are covalently bonded. So if we had one molecule of SO3, okay, if we had one molecule of SO3, how many atoms would be in there? It's pretty easy, right? We have 1 sulfur and 3 oxygens. That's 4 total atoms. So this actually is a 2-step conversion. We're going to go from moles of SO3 to molecules of SO3 to atoms. Okay? So this conversion factor is easy to know. This one is, you just kind of have to think about it and understand that you have to think about how many atoms are in a molecule. Okay? So we're going to start off with moles of SO3. We're going to use this conversion first because it has moles in it. We're going to put the 1 mole of SO3 on the bottom because we want that to cancel with the moles of SO3 we're starting with. The 6.02 times 10 to the 23rd molecules will go up here. Okay, so moles of SO3 will cancel with moles of SO3. This conversion factor is used, so we're done. Now that we're in molecules, this second conversion, we're going to take 1 molecule of SO3 and put it on the bottom because we have molecules up top. The 4 atoms then will be on the top of our fraction. Okay, so molecules of SO3 are going to cancel with molecules. And now we are in the unit of atoms, which is what they are looking for. And so now we just need to do the math out and get an actual number. So let's take 1.14 times 6.02 double E 23 equals times 4, and then divide by 1, which we're not going to do because that's not really going to change anything. So using significant figures, our starting number was 3 significant figures. So we're going to round this to 3 sig figs. So this is going to be 2.7, and then the 4 is going to round up to a 5. So 2.75 times 10 to the 24th. Okay, the E means times 10. The 24 is an exponent. So we're going to have 2.75 times 10 to the 24th atoms. That is the answer that they are looking for. Okay, that's how many atoms are in 1.14 moles of SO3. So again, let's go type that into our notes here. So we have 2.75 times 10 to the 24th. And let's get rid of some space here. There you go. Okay, so this is the number of atoms that they're looking for. A little bit tricky just because of the units. This is in molecules. So All right, moving on. Number 7, how many representative particles are in 2.5 moles of H2O2? All right, so this is just like other ones we've already done. We are starting with 2.5 moles of of H2, that's also not what I'm trying to do, O2, and we are getting this into representative particles. The representative particles in this case are going to be molecules of H2O2 because H2O2 is a molecular compound. These are both nonmetals. So this is a covalent compound, therefore it exists as molecules. Okay, so we're just going from moles to molecules. This is a one-step problem, very simple. Let's switch to our paper here to do the math out. So again, let's write out our information. We have 2.5 moles of H2O2. We are converting that into molecules of H2O2. And to convert from moles of a material to molecules, we will need to use Avogadro's number. So 6.02 times 10 to the 23rd. The unit on this is going to be molecules of H2O2 because that is the kind of particle that this exists as. And this is for, of course, every 1 mole of H2O2. Okay, so here's our conversion factor. This is the only conversion factor we need to use because we are starting with moles and we're going to molecules, and this has both of those units in it. So since we're starting with moles of H2O2 on the top of our fraction, we're going to write 1 mole of H2O2 on the bottom of our fraction, and the 6.02 times 10 to the 23rd molecules on the top. So this way, moles of H2O2 are going to cancel, and then we will get into molecules, and this is just going to be a simple multiplication problem. So we will take 2.5 times 6.02 double E 23 equals, and counting significant figures, we're going to round to 2 significant figures because 2.5 has 2 significant figures. So this would be just 1.5 times 10 to the 24th. Okay, so 1.5 times 10 to the 24th molecules of H2O2 is the answer that they are looking for. All right, so let's go back to our notes and let's put that in here. So 1.5 times 10 to the 24th molecules. There we go. That is our answer. All right. All right, we got about 4 more problems left. Here we go. Number 8, find the molar mass of PCl3. All right, so molar mass. Molar mass can be found by looking at the periodic table. So I am going to pull up a periodic table here real quick because we're going to need to look at one. And if you have yours on hand, that would be good. If you don't, I would recommend probably pausing the video and then going to get it because you're going to need the periodic table for this. All right. So give me 1 second here to pull this up. This is my fault for not having this prepared in advance. Sorry, guys. And here we go. Let's see here. So, all right, we're going to cut to my lovely face. There I am. Let's pull up a periodic table here. Perfect. Okay. So let's zoom in a little bit maybe on this because these numbers are kind of hard to see. Does that work better? Yes, it does. All right, wonderful. Okay, so let's go back to our notes. So it says, find the molar mass of PCl3. All right, so to do this, we're going to need to find phosphorus, which is P, and chlorine, which is Cl, on the periodic table, and we're going to need to look at their molar masses, and then we're going to need to add them together, okay? So we're going to insert a text box first in here so we can do some typing. Change our font size, change our color, okay? So P is going to be equal to, and then Cl, and I guess 3 is going to be equal to. All right, so let's go look at our periodic table here, okay? All right, so phosphorus is here. So phosphorus has a mass of 30.974. If you want to take it exactly as it is, you can. I'm just going to round it to 31 because it's very close to 31, and right now we're not trying to be super precise because the problem doesn't really care that much about being precise. So we're going to say that phosphorus is 31 grams. And chlorine, again, let's go look back at our periodic table. Chlorine is over here. This is 35.453. Now this one isn't close enough to a whole number for me to comfortably round it to like 36. So I'm just going to keep it as 35.5. I'll just say 35.5. Okay, so let's just say that chlorine is 35.5 grams, but we need to times that by 3 because there are 3 of them in this. And I don't know why I put that 3 up there. That 3 should not be up there. It should be down below. There we go. Okay, so we're going to times that by 3. So let me do this in a calculator here real quick because I don't know what this is off the top of my head. 35.5 times 3. This is 106.5 grams. And then we are going to take these two and we're going to add them together. Okay, so 31 grams. 31 grams. Oops, let's undo that. 31 grams plus 106.5 grams equals, and this will tell us our molar mass. So I get 137.5 grams is the molar mass. Okay, so all we're doing is we're just simply adding together masses on the periodic table to get our molar mass for the compound. Super, super simple. All right, taking a look at number 9. What is the molar mass of ethane, C2H6? Okay, so same thing as the previous one. We're going to need to look at a periodic table. So carbon, we're going to look at our periodic table here. Carbon is over here. Carbon has a mass of, let's just say 12. And hydrogen, of course, being over here, has a mass of basically 1. So carbon, and there's 6 of them here. So, or sorry, 2 of them. So C2. So this is 12 grams times that by 2, which is equal to 24 grams. And then H6, which is 1 gram times that by 6. So that's equal to 6 grams. And then if we add those together, so 24 grams plus 6 grams equals, we get a molar mass of about 30 grams. Okay, that's it. Again, super easy. We're just adding some numbers together. All right, number 10, find the mass of 3.65 times 10 to the negative second moles of K2SO4. All right, so this one is, this is actually a little bit of a harder problem because this section of notes hasn't gone over converting between grams and moles. But if we realize that molar mass is a fraction, this problem actually is not too difficult. So they are asking us, and actually, you know what, we're going to take this question 11 here. I'm going to put this on a separate page because we are going to need to use some space here. So let's just do a duplicate slide here real quick. Let's delete all this, paste that in there. There we go. And then let's get rid of this so we have some space. All right. So we are starting with 3.65 times 10 to the negative second moles of K2SO4, and we are going to convert this into grams of K2SO4. Okay. Now to do that, we need to know how many grams are in 1 mole of this material. And that, by definition, is the molar mass. That is what we just did up here in these previous problems. So let's look at a periodic table. Let's find the molar mass for this K2SO4. Okay, so molar mass of K2SO4 is going to be equal to. So we're going to find the molar mass, then we're going to use that to do a conversion. Okay, so let's take a look at our periodic table. So potassium has a mass of about 39. Okay, it's 39.098. We're just going to say 39 because it's easier to do it as a whole number. Sulfur is 32.065, so basically 32, and oxygen is 16. So let's go to our notes. So this is going to be 39 grams for the potassiums, times that by 2. Okay, so let's maybe make this out better. So let's go. Potassium K2 is equal to 39 grams times 2. All right. Sulfur was about 32 grams, and then oxygen, or O4, 4 is equal to 16 grams times that by 4 equals. And then we'll add all these together. Okay. So 39 times 2. This is 78 grams. 16 times 4, I probably should be able to do this in my head, but I'm going to do it on a calculator anyway, just to be safe. This is 64 grams. And then if we add all these together, so 78 plus 32 plus 64. So 78 plus 32 plus 64, we get 174 grams per mole. So 174 grams per 1 mole. Okay, this is our molar mass. This is a conversion factor. We can use this. Oh, I did not mean to do that. That's what I meant to do. We can use this to convert. Okay, so we're going to switch over to paper here. I'm going to write out all the information that we know, and here's how we're going to do this problem. Pretty simple. So we have 3.65 times 10 to the negative second moles of K2SO4. All right? And we are going to convert this into grams of K2SO4. And we know that 174 grams of K2SO4 is equal to 1 mole of K2SO4. That's the molar mass. We just calculated that. Right? Now this conversion factor that we have here can go from moles to grams. We're starting in moles, we're going to grams. So this moles of K2SO4 that we're starting with, we need to put this 1 mole on the bottom so that it cancels. So 1 mole of K2SO4 will go down here. The 174 grams then will go on the top. And we have it this way so that moles of K2SO4 cancel out with each other, like this. And the unit then that we're left with is grams, which is exactly what we want in our answer. Okay? So all we're going to do is on our calculator, we are going to take 3.65 double E, and then it's going to be negative 2. So negative 2 equals, okay, so here's our number in regular notation, times 174. And then we can divide by 1 if you really want to, but we're not going to. Okay? And then looking at significant figures, this is 3 significant figures. We need to round this to 3, so we're going to have 6.35. That's our 3 sig figs. So 6.35 grams of K2SO4 is the final answer that we are looking for. Okay? So this section of notes didn't really have that process lined out, but I mean, we've been doing conversions with moles and particles. We're pretty much doing the same thing. We're just using a different conversion factor. So 6.35 grams of K2SO4, that is our answer that we are looking for. All right, last question. Calculate the molar mass of ammonium nitrate. All right, so this is just a molar mass problem. The tricky thing with it is they're not giving us the chemical formula for ammonium nitrate. We have to be able to write it. So if we can write the chemical formula for it, we can find molar mass. So ammonium has a chemical formula of NH4 and a charge of +1. Nitrate is a polyatomic ion. It has a chemical formula of NO3 and a charge of -1. So if we put these together, ammonium nitrate then is going to be NH4 NO3. Okay, 1 NH4 will bond with 1 NO3. They each have a charge of +1, -1, so those will just balance each other out right away, so we just need 1 of each. So now from here, we need to then find on the periodic table the mass of 2 nitrogens. Okay, so there's 2 nitrogens. We need to find the mass of 4 hydrogens and 3 oxygens. Okay, so looking at our periodic table, nitrogen is over here. So nitrogen has a mass of about 14 grams. So let's go look back at our notes. So nitrogen is 14 grams, times that by 2, because there are 2 of them. So that's 28 grams. Hydrogen has a mass of basically 1. So 1 gram times that by 4, so that's 4 grams. And then oxygen, again, looking at our periodic table, has a mass of 15.999. We're just going to say 16 to make it easy. So oxygen is 16 grams, times that by 3. So let me do this on a calculator, even though I should be able to do it in my head. That's okay. So 16 times that by 3, that is 48 grams. And then we add them all together to get our total. Okay, so molar mass is going to be equal to 28 plus 4 plus 48, and that is 80 grams per 1 mole. Okay, that is our molar mass. Bam. There's our final answer. All right, so those are all of the questions for the notes here for Chapter 10, Section 1. Hopefully that helped to clear up some confusion for you, but as always, if you ever need any more help or have any questions, you can always reach out to me. All right, guys, I will see you in the next video. Bye.